3.8, tomorrow we'll do section 3.8. How many of you guys have taken physics or are taking physics currently? There'll be a decent amount of overlap between what we do today and things you guys have learned in physics in the past. Well, we've spent some time in the past in this class talking about position, velocity, and acceleration, but not a ton of time. So today we'll kind of talk about that, but we'll talk specifically about something called rectilinear motion, which is movement of a particle bound to an axis or a straight line, okay? Typically we talk about it with respect to the x-axis, okay? So let's review some things about velocity and acceleration that you guys probably have seen before, but we got to review it before we launch into this stuff, okay? So again, rectilinear motion is just movement along a straight line. So like I said, usually we do it with respect to the x-axis, okay? And then things you guys have seen before would be our position function, our velocity, and then we'll talk about acceleration here in a second, okay? So our position function, usually called s of t, but also sometimes called x of t, just gives you your position or your distance, okay? Make sure everyone's here real quick. Just Armand and Tessa that were missing. Okay. All right. And then let's talk velocity, okay? So I should say position usually called s of t, or I'm going to put x of t as well there because you may see it as x of t as well. But for the rest of the lecture, I'm going to just call it s of t, okay? All right, and then average velocity. So we're going to talk about the difference between average and instantaneous. We've already talked about that before, so I don't think this will be anything groundbreaking. Our average velocity is just the slope of our secant line. So it's our change in s divided by change in t, which if we shake that out in terms of practical application, that's our change in position over change in time. What do we call a change in position? What is that called? Displacement, right? Oh, yeah. So displacement is our change in position, okay? And then our instantaneous velocity is the rate at which our velocity is changing at a specific time, okay? So we find that by taking our derivative and evaluating it for whatever that timestamp is, and that's the slope of our tangent line to our position function. So slope of our tangent line, s prime of t is equal to v of t, which is the derivative of the position function evaluated at time t. When our velocity is positive, that means we're moving in a positive direction. So which two directions would we consider to be positive? Up and right. So moving to the right, which is typically what we'll be talking about in this section, gives us positive velocity. Okay, so when we have a positive velocity, we know that our particle is going to be moving to the right. And so if our velocity is negative, that means our particle is moving either down or to the left. In this section, we'll talk about it particularly in terms of moving left. Okay. Speed and velocity are very closely related. How are they related? Speed is just the absolute value of velocity, okay? We don't talk about negative speed. We don't have negative speed. Our speed is always positive, but it's going to be the absolute value of our velocity, okay? So if I want a function for speed, I would just do the absolute value of our velocity function. If I wanted a graph for speed, I would look at my graph for velocity, and any of my negative values, I would reflect over the x-axis and then make them positive. Okay, acceleration. So our acceleration is the rate at which our velocity is changing. I mean, you can write that down if you'd like, but you have to understand, like, anytime, we get from one level to the next, to go from velocity to acceleration, we have to take the derivative, so it's the rate at which that thing is changing. So it's the rate at which our velocity is changing. So write that if you want, you don't have to. I kind of spell that out down below if you read between the lines. So if you take the second derivative of your position function, which is the first derivative of your velocity function, that gives you a of t, which is your acceleration function. Now, this part is important as it's a little tricky the first time you look at it. And I'm curious how much overlap there is between this and physics. Because can I be real with you guys? I've never taken a physics class. which seems crazy considering what I teach. There's a ton of overlap between the two topics, but I've never taken a physics class, not in high school, not in college. Okay. If our acceleration is positive, that means our velocity is changing in a positive direction. Since my velocity is just our rate of change of since our acceleration is the rate of change of our velocity, if we have positive acceleration, that means we are changing in a positive direction. Okay. That doesn't mean we're moving in a positive direction. That just means we're changing in a positive direction. There's a difference between the two things. It's a tough thing to wrap your brain around. And then, of course, if your acceleration is negative, that means your velocity is changing in a negative direction. Okay? So what acceleration can be helpful for, because velocity already ties up, hey, am I moving to the right or am I moving to the left? That's what velocity tells me. Acceleration is helpful in telling me if my particle is speeding up or if it's slowing down. Okay? All right. So that happens dependent upon the sign of my velocity and my acceleration. If they have the same sign, so if my velocity and acceleration are the same sign, then my object will be what? Speeding up. Do we learn that or something related to that in physics?
It's moving away from the x-axis.
You say it's moving away. Okay. But you in class you've mentioned it's speeding up before? Okay. If they're the opposite signs, then what's it doing?
Going towards the x-axis.
Yep. Or we would say it is slowing down. Okay. All right. So it's slowing down. Okay. Now, let's talk about why that's the case. So if our velocity is positive, that means it's moving to the right. If our acceleration is positive, that means it's changing in a positive direction. Our velocity is changing in a positive direction. Okay? So what that means is, since it's already going to the right and is changing in a positive direction, it's speeding up. Okay? If my velocity is negative and my acceleration is negative, my velocity is negative, I'm going in a negative direction. If my acceleration is negative, it's changing in a negative direction, so I'm like picking up speed in a negative direction. Okay? But let's say our velocity is positive and our acceleration is negative. So I have positive velocity, but the rate at which my velocity is changing is negative, which means my velocity is then going to be decreasing. So because of that, would my particle be speeding up or slowing down? If I'm moving in a positive direction, but the rate at which it's changing is decreasing,
Slowing down.
it's slowing down. Okay? So they're working against each other. And then same thing, if I'm moving in a negative direction, but the rate at which it's changing is positive, those things are working against each other, and it makes my object slow down. Okay? All right, so that is a major key. Okay? All right, so let's use that and put some of these on a number line and look at some graphs of things. I made a business decision last night. Either I could recreate all of these graphs using LaTeX and some screen captures from Desmos, or I could just borrow some Gillette graphs, and that is what I did. So to pay homage to the GOAT, all these are going to be, a lot of these are going to be some Gillette graphs that I copied. Okay, so given the following graph, so we don't have a function, we just have the graph. We want to answer the questions as best we can. We want to figure out when our particle is moving to the right, where it's stopping at, and where it's moving to the left. And then we're going to draw the path on a number line. Okay? All right. Now, drawing on a number line is going to be probably different than anything you guys have seen before, but it's a good telltale of what's happening with our particle. Okay? So let's just start simple. Where is my particle moving to the right? What would need to be the case for my particle to be moving to the right? Okay, so velocity is greater than 0, okay, which means the slope of our tangent line of our function s has to be positive. Where does that happen from? 0 to 3. Good. So on the interval from 0 to 3, then that means I'm going to have a positive velocity and my particle is moving to the right. It starts at -6, but then it's moving to the right until I get to time t equals 3. And what happens at 3? It stops. Okay, so at t equals 3, it stops. And then it's moving to the left where? From what to what? I got some arrows down there, so we're going to say 3 to infinity. Okay, so from 3 to the infinity, then my particle has turned around and is then moving to the left. Okay, so if I draw that, my S value starts at what? -6. So my S value starts at -6. Let's just put some values on here. I think skipping by 2s is the move. All right, so I start at -6. Now what I'm going to do, really, here's what's happening, okay? And I don't know how well you can see it. What's happening is my particle starts at -6, it moves to the right, and then it moves to the left. But like, I can't really draw that on a number line because then it just looks like back and forth motion. You know what I mean? That's not really doing us any good, okay? So because of that, what I'm going to do is once I start changing direction, I'm going to pick up my particle and I'm going to draw it like going backwards. So I'll start at 6. And then that happens until I get to what value of S? Where I move to the right. Because first I move to the right until I get to what value of S? 6. So from here to 6, it is moving to the right, and then it turns around. So I'm going to draw my graph going like that, because then after that it moves to the left fully. Okay? So this is my version of drawing it. Really, this is like also how Mrs. G does it as well too. But that's how we're going to draw that path on a number line. Okay? If I just went like this and then this, like you can't really see that very well on the number line, so we're going to give it some depth. Even though it's important you understand that that particle is completely bound to that axis and it's not moving. Okay? All right. So this is, what time value is this where it is turning around? We said that's t equals 3, right? Okay. Now, can we pick out from this graph? The answer is yes. Can we pick out from this graph when our particle starts to slow down?
Yeah.
Where does that happen at? What do you think? At what t value? I would say 1.5. Okay? In grading your test, I saw that we need a little bit of help with picking out these values. What is this called? Very good. That's our point of inflection, right? That's where our second derivative changes sign. Okay? So at t equals 1.5 is where my particle starts to do what? Slow down. Okay? Now, let's talk about signs. Okay? My derivative is positive here because, yeah, of course, my function is increasing. So we've got positive derivative signs there. But talk to me about the sign of our second derivative, aka our concavity, right? What concavity does our function have from 0? We said it changes at 1.5. So then from 0 to 1.5, it's positive. So we would say it is concave up, right? But what we really care about is the fact that it's positive, okay? So a of t is greater than 0 here. But then, what happens once I get to the right of 1.5?
Negative.
You're right. It's negative. So here, our concavity, it's concave down. So it's negative. That happens from what value to what value?
Just 1.5 to
1.5 to, what do we want to call this? Like 5, right? I mean, it's concave down here, but at some point, well, it's actually not going to turn back around. So actually, it's just going to be concave down on the rest of that interval, okay? All right, so then that means we start slowing down at 1.5. So we'd say it's speeding up. And then what value does that happen at where it switches from speeding up to slowing down? What t value?
1.5.
Okay. What about what s value? At 0. So then that means here we switch from speeding up to now it is slowing down. Okay. I tried to draw it like where it's lifting off the x-axis there to kind of indicate that it's slowing down. Okay. But then once I hit this apex here, now it is speeding up on the top part of our path along that number line. Or I said speeding down. That's crazy. Speeding up. Okay. All right. Questions there? Let's do it with a function now. All right, so given s of t equals t cubed minus 6t squared, for t greater than or equal to 0, we want to find the direction of s of t, meaning is it moving to the left, moving to the right, and then determine whether the object is slowing down or speeding up, okay? What's my first move? I should start by doing what? Derivative, because I want to figure out is it moving to the left or is it moving to the right? Depends on our velocity. So s prime of t equals v of t, which equals 12, no, I lied to you. 3t squared minus 12t. Okay? Now, in order to figure out the sign of my velocity, how should I proceed? What should I do next? What do you think?
Set equals 0.
Set equal to 0 and then perform a sign analysis, right? Okay, cool. So 0. All right, so I'm going to factor out 3t, and then I'm left with t minus 4. All right, so if I set both equal to 0, I get t equals 0, and I get t equals 4. All right?
Yeah.
Okay, sign analysis time. Now, I should say this as well, too. We have that t is greater than or equal to 0. So when I do my sign analysis, I don't need to worry about anything to the left of 0. Okay? So I've got 0 here, and then I'm going to put 4 right there. Okay. So my values in between 0 and 4, will that output a positive or negative for my derivative? A negative, right? Because I would have a negative value. I'm looking at right here. I'd have a negative value at first, and then, a positive value, and then hit with a negative value. So I get negative values for my velocity. Okay. That means we're moving to the left. And then to the right of 4, nothing but positivity, right? So I'd be moving to the right. Okay. All right, so we are moving left from 0 to 4. So we start out moving left, and then we are moving right from 4 to infinity. Okay, so there's my movement. Now I want to figure out if it's slowing down or speeding up. I need the acceleration to help me figure that out. So now I do s double prime of t, which is v prime of t, which is a of t. So we want to figure out the sign of our acceleration, which will tell us where is my velocity increasing and where is my velocity decreasing. Okay? All right, so a of t is just going to be the derivative of this guy right here. So I would get 6t minus 12. Jay would advocate for us to do a sign analysis again. I get that my t value is going to equal 2 if I set that equal to 0, and then let's do a sign analysis. I'm going to stack my sign analysis for my acceleration underneath my sign analysis for my velocity. You'll see why here in a second. All right. What value do I care about in terms of t? 2. I'm going to put 0 on there as well too, but I'm going to put 2. And I'm going to try to do it with the same scale as the number line that I did up above. That'll make my next part after this much easier. All right, if I plug in a value between 0 and 2, would I get positive or negative outputs for my acceleration? Plugging it into here, it would be negative values, right? And then if I plug in a value to the right of 2, so 6 times 3 minus 12 is going to give me positive values, okay? All right, now, we already figured out movement. That's bound to velocity. Acceleration just tells me where my velocity is increasing or decreasing, okay? All right, now, what I'm looking for, because I want to figure out where it is slowing down and where it is speeding up. And again, I need to know the sign of both my velocity and my acceleration in order to figure that out, okay? All right, so I look at, between these two sign analyses, I think that's the plural of analysis, I don't know. Where do they have the same sign? 0 to 2. Both of them are going to be negative from 0 to 2. So then what would we say our particle is doing from 0 to 2? Speeding up. Good. All right. So obviously it starts slowing down after 2. Would you guys agree with that? Where does that happen from? 2 to 4, because both of my velocity, or I should say my velocity and my acceleration have opposite sides. My acceleration is positive from 2 to infinity, but my velocity is negative from 2 to 4. It's negative from 0 to 4, but 2 falls within that interval. So you got to keep that in play. All right, and then after that, what does my particle do? Speeding up from 4 to infinity. Okay, I know my acceleration changes to positive after 2, but my velocity doesn't catch up until I get to the t value of 4. Okay? All right. Questions there? Let's look at what that looks like on a graph. Okay, so I want to graph a bunch of things. So using the last example, same function, let's graph each one of these things. Okay? All right, so the first thing I want to graph is S of t. Now, in order for us to get an actual decent graph of S of t, we should make at least a table with some values for the ones that we care about, okay? So if I do t and then S of t, that way we can make a pretty decent graph. Well, I can think of S of t like this. If I factor out a t squared, it's t squared times t minus 6. What is that going to look like? What are my x-intercepts? 0 and 6, right? Okay. Now, what type of roots do I have at 0 and at 6? At 0, I have a repeated root, a double root. You guys agree? What happens to the graph at that value? It bounces off there, right? So I don't really care about the left side of that. I just care about the right side of that. Now, if I think of end behavior, as my t value goes to infinity, since I have t cubed and it's positive, my end behavior is as t goes to infinity, S of t is also going to go to positive infinity as well too, okay? That means it's got to cross through this axis and go up to infinity because this is a single root at 6. At 0, you guys told me it bounces, so I'm assuming it's going to look something like this. Okay, a couple things stick out to me. It looks like to me we have some sort of change in concavity between 0 and 6. Would you guys agree? I don't know exactly at what point. Actually, I kind of do. But at some point we change concavity. So that's why I drew the graph in such a way that it looks like that. Okay. All right, so there's a rough graph of S. We can add more to it here in a minute. Let's graph what V looks like, okay? So again, we said our velocity function V of t was equal to, I don't have to look back and just look at this, 3t squared minus 12t. Or you could think about it like 3t times t minus 4, giving us x-intercepts of what? Good. So 0 and 4. My end behavior to the right is the same. To the left it would change, but I don't care about to the left. I just care about to the right. Okay? It's still going to go to positive infinity because I have t squared and it's a positive leading coefficient. Okay? Which means my graph is going to look something like this. Okay? Do we have any sort of change in concavity of that? No. That should be concave up throughout. Okay? Now, I also want to graph absolute value of V, which what does that tell me again? Very good. So how do I use the graph of V to help me graph absolute value of V? Just reflect it over the x, right? I take any values that was below the x-axis, I reflect it over the x, okay? So I still have the important point of 4, but my graph, instead of going down, is going to look something like this first, and then it's going to go like that. Okay. All right, so that's my speed, which means my speed is positive there, and then I stop for a second, and then it continues on again, okay? Now, my acceleration function was 6t minus 12. So I have a y-intercept of negative 12 and then a slope of 6. Where did I cross the x-axis again? 2. So it's going to look just like a linear graph like that, okay? All right, so I have a negative acceleration first and then a positive acceleration on the other side of 2. Let's go ahead and update our graph a little bit. So t equals 2 is what graphical feature in my original function? Point of inflection, because my second derivative is 0 there, okay? So this would be like 2, I guess, would be this point of inflection here. All right, and then what is t equals 4? What graphical feature is that? That would be my min, right? That would be where my velocity changes sign, which would be where my particle changes direction, okay? All right, so then this is going to be our min, okay? All right, now let's answer some questions, and then we will draw our graph draw the path on a number line. Where's my particle to the left of the origin? Because again, this is just bound to an axis and it's moving to the left and the right. So on what interval will it be to the left of the origin?
Where it's negative, so 0 to 6.
Where s of t is negative, so from 0 to 6. So I would say from 0 to 6, it would be to the left of the origin. Where is it to the right of the origin then? Good. I'm going to write this in red, indicating we get it from the graph that is red. Okay, so from 0 to 6. This looks bad. I thought I erased it. All right. And then it is right of the origin from 6 to infinity, okay? Where is my graph moving to the right? We answered that question already. What did we say?
4 to positive.
4 to infinity. And again, you could look at the graph in blue to get that as well too, because that is where my velocity is going to be positive. So from 4 to infinity. Good. All right. Where is it moving to the left?
0.
From 0 to 4. Very good. Okay. Now, we need to talk about when it's speeding up. Where do we say our graph was speeding up?
0 to 2 and 4 positive.
Good. 0 to 2, and then 4 to infinity. And then we said it's slowing down between 2 and 4, because then I would have opposite signs between those two. Okay? All right. Now what I want to do is I want to plot this on a number line. Okay? So this is S. And then we're going to put our t values. We're going to draw those when we draw the solution curve itself. Okay? All right. Now, as far as S goes, we should get some values for S. Okay? So what important t values should we pick out our values of S? Like what graphical features should I put on my graph? Obviously, at the time values of 0 and 6, I need that, right? What is the output for S of t at 0 and 6? Yeah, each one of those are 0 because it's my x-intercept. What other feature, though, like turning around is probably important, right?
Oh, yeah,
So
so 4.
4.
And then 2.
Okay. So if I plug in 4, I need to plug it into my position function. So here or here, whatever you want to do.
Negative 32.
Negative 32. Good. Probably wouldn't be a bad idea to figure out what happens at 2, right? Because that's our concavity. That's worth putting on there. So we can figure out, where it's...
Negative 16.
You said what? Negative 16?
Yeah.
Okay. All right. So these are the values that I want to make sure I call out on my graph. Okay? So I go from 0, and then I go as far left as negative 32. And then we could put negative 16 there as well too. Okay? So my particle starts out at 0, moving to the left. Okay? So I'm going to start at 0, and I'm moving to the left. Once I get to the S value of negative 16, that's where I start changing my direction a little bit. Okay? Until I reach that value at negative 32. And then where does my particle go? To the right. So I indicate that it changes direction. I don't like how I wrote that part. changes direction, and then moves to the right. Okay? But let's put our time values in. So this would be at t equals 2. And then this would be at t equals 4. We said it's speeding up. And then it starts slowing down. And then once we get past 4, we said it was speeding up again. Okay? These graphs are weird because it's like, you know, S, your Y value, it shows the outputs on the horizontal axis, and then we are putting our T values in on those solution curves. So they take a bit of practice to do in the beginning, okay? All right. I didn't get as far as I wanted to, but it's quiz time. So grab a calculator. I had another example that was similar to that, just does more things, but I did more of that example